Hi, we're going to talk today about high-resolution 3D tunnel seismic reflection. And the site that I'm going to present is Olkiluoto in Finland. It's the site of the high-level nuclear waste repository, which the Finnish energy companies are setting for disposal of the high-level nuclear waste. First, I would like to establish some connection between tunnel seismics and nuclear disposal. Posiva, which is the Finnish nuclear waste operator, and SKB, which is the Swedish counterpart, have opted for spent nuclear fuel disposal in crystalline bedrock. The rock mass surrounding the disposal facility is considered to be a crucial element preventing radionuclide transport to the biosphere. The long-term safety of the disposal focuses on the hydraulic conductivity of the rock mass, which needs to be minimized. Geological features with transmissivities higher than the average rock are not accepted for disposal. Besides increased hydraulic conductivity, deformation zones and continuous single fractures constitute a potential risk for secondary movement and can result in sharing of the disposal canisters as a result of seismic events. In conclusion, tunnel seismic is one of the methods considered for identifying and characterizing potentially hazardous rock features. We'll go now to a bit of history. Tunnel seismics for nuclear waste disposal has a beginning, at least the one that I have been involved with, in 1980, when the SRIPA project has been set by the OECD and the Nuclear Energy Agency to as an international research effort based as main laboratory at the SRIPA mine, which is an abandoned copper mine in central Sweden. The SRIPA project has been the testing ground for the development of techniques and methodologies for site characterization for a nuclear geological repository. One of the project objectives was to test the predictive capabilities of newly developed by then radar and seismic tunnel and borehole characterization methods. Taking the follow from SRIPA, the Grimsel test site in Switzerland, operated by Nagra, started the research into investigating the potential of geophysical remote sensing methods to predict discontinuities ahead and around the tunnel face. We're going to show you now what we are doing in those days and how the things have evolved towards our times. In the slide which you see now on the screen, we present on the left upper corner a shot gather obtained from a source and a receiver array placed on the tunnel wall. The key processing step to this layout is the image point transform, which has the capability of turning hyperbolic events in the shot gather into well-defined vicinities of high amplitude in the transform space. These vicinities, they are in fact easy to migrate into the normal space directly, and they will give locations of the reflectors in the 3D space directly. The particularity of the image space is that it can be filtered and turned by selecting only the highest amplitudes into a series of discrete dots which correspond to the most prominent features of the site. And when these features are migrated, as we see on the lower line towards the right, the result is a map of the most prominent seismic features of the site with respect to the tunnel, which we can see here at the bottom. Well, this was the situation in 1992, and the methods evolved quite a bit since, but the principles are very similar to what it was then. Coming back to Finland now, the nuclear waste repositories at Olkiluoto started to be excavated in the year 2004. And the access tunnel has been ever since been used as a research and demonstration facility for programs conducted during the construction of the spent nuclear fuel repository, and which include bedrock characterizations, geology, geophysics, hydrogeology, geochemistry. These studies are primarily meant to ensure that the bedrock is suitable for the final disposal. These also help identify areas where the final disposal tunnels would be most cost-effectively be placed. Regarding geophysics, its main role at Onkalo is the detection and characterization of the fracture and deformation zones. More about Onkalo. The seismic imaging, electrical and electromagnetic soundings are the geophysical methods found most suitable for detecting long fractures. On one side, seismic investigations best describe mechanical discontinuities. The resolution and depth penetration has been considered adequate for detecting long fractures and for their continuation. On the other hand, electrical and electromagnetic methods give information on lithological variations and foliation. The objectives of the tunnel seismic project were to image long faults and fractures at the side, ahead, and below or above the tunnel, to draw a velocity profile along the tunnel wall, to compare seismic results with other geophysical determinations, for instance electric, and to verify and evaluate the agreement of the seismic predictions with geological, geomechanical, and hydrogeological models, update these models based on the seismic information. There were two sessions of seismic measurements at Olkiluoto in the Onkalo. In fact, there is a third one which is just going on in 2013, but results are not reported yet. So we're going to talk today about the previous two. The first session took place in 2007 along a stretch of a tunnel of 100 meters at the chainage 7,720 to 1,820 meters along the tunnel. The second session took place 2 years later in 2009 over a section of 300 meters length between the chainage 3,500 and 3,800 meters. Besides the scientific aspects which could be discussed, and we will, there were a number of practical goals that were set. Namely, these measurements, they have to become part of the measuring program of the nuclear repository construction. Therefore, the measurements must be performed during the breaks of the normal tunnel construction operations, with no additional standby times, which may result from the construction work. The investigation depth should be of the order of at least 100 meters to allow enough time for data processing and interpretation before the tunnel arrives at the located discontinuities. The preparation for the measurement should not interrupt or interfere with the construction work. The method should be applicable for conventional drill and blast tunnels, but also for full-face drilling. We are going now to go briefly through the equipment used at Onkalo for the seismic measurements. There were three types of sources for the tunnel wall, as well as two types of receivers, one used in 2007, the other one in 2009. Regarding the sources, we started with the handheld electric percussion hammer. Then we have been using a boomer, a drilling boomer, which was part of the normal tunnel drilling equipment. So we thought it would be a very good idea to use standard equipment found on the tunnel construction sites as seismic sources for the future. And thirdly, we used a source which was slightly larger, or actually significantly larger than the handheld used in 2007, which we term it to be the VIPSYS 2050 because it would emit some 200-250 joules per blow. In comparison, the handheld electric hammer used in 2007 emitted 20 joules per blow. The receivers were placed in short holes in both situations. In 2007 there were two components. One component was vertical, the other one was horizontal, but both of them parallel with the tunnel wall. In 2009 we added a third component, which was perpendicular to the tunnel wall. So therefore in 2009 we are recording upwards parallel to the tunnel face, horizontal parallel to the tunnel face, and within the rock perpendicular to the tunnel face. If we look on the right side of the slide of the frequencies that each of these sources developed, we see that each of them reaches beyond 1 kilohertz with slight differences. For instance, the boomer has the most localized spectrum in two regions, while the VIPSYS 250 had the most linear spectrum of the three. Of course, when the VIPSYS 250 was used on the floor, as we can see here in the fourth graph, the frequency spectrum was limited upwards due to the gravel on the tunnel floor, as opposed to the wall where the source hit directly towards the rock. Now these sources, they are time distributed sources. There is a series of impacts in rapid sequence, which is emitted by the source, and then is decoded into a normal looking seismogram. I will give you an impression by showing a short movie of the sounds and looks of the source when it is in action. So what you hear now is the series of impacts which I was talking about. In the beginning, the impact rate is slower and it gets faster towards the end, in such a way that the result is a non-repeatable sequence, which can afterwards be decoded and deconvolved to a short, normal-looking seismogram. We are going to look now to how the waves emitted by the source in this environment are going to propagate around and the head of the tunnel. What we have here is a synthetic example with the source placed on the side of the tunnel, as we see in graph number 1 here, which presents a snapshot at 1 millisecond after the action of the source. We can see at 3 milliseconds the wavefront developing and developing forward at 5 milliseconds and so on. What we can also see is that we do have some remnant energy which is trapped near the tunnel. These are waves which are surface waves and will travel along the tunnel and also around the tunnel on the tunnel surface. As we see in the following graph, the tunnel waves manage to arrive on the other side of the tunnel and they keep on circling the tunnel. However, in the end, as we reach 15 milliseconds, we have a front which is fairly nice and well defined, leaving the tunnel area towards the rest of the rock, but we still have some remnant energy going back and forth on the tunnel surface, creating some mild ringing. The situation changes somewhat if we add to the tunnel a feature which it definitely has, is the excavation disturbed zone, or EDZ. This is a feature consisting of a low velocity cracked rock bordering the tunnel. It's not a very wide zone. At Olkiluoto, this zone does not go over 0.3 to 0.5 meters, but it goes all around the tunnel. Now, in this situation, hitting on the wall with the source will generate the same type of propagation in the beginning, but very soon the energy trapped in the vicinity of the tunnel becomes significant. And it stays so until, as we see in this graph, secondary sources are created. And the complexity of the wave field goes on and on. This complexity is manifest in terms of ringing. So this energy trapped along the tunnel is going to travel back and forth, creating a very stripy look to the seismograms. Something like shown in these pair of graphs. On the left, we do have the raw shot gathers, an example of raw shot gather, which, as we can see, it is heavily contaminated by ringing parallel to the S arrival. This is actually happens to be also the velocity of the tunnel wave, which is very close to the S wave. And we can see that later scatterers, later arrivals, are virtually completely masked by this ringing. However, based on the modeling which we showed before, we were able to design a filter which could take off most of the ringing, leaving later arrivals and scatterers to be seen. Then again, the picture of the right versus the picture on the left is different only in that respect that the ringing has been removed by a model-driven filter, which assumes a velocity for the tunnel waves and also a way of propagation ahead and around the tunnel that has been checked and verified by modeling. Now, once this is done, we're going to look a bit at what happens actually with the waves propagating along the tunnel. For this purpose, we made inversions, velocity inversions of both P and S waves, as we see in the upper two graphs. And what is noticeable here is that we do have a low velocity layer in the immediate velocity of the surface of the tunnel for both P waves and S waves. This is the disturbed zone, the excavation disturbed zone. With the density of the rocks taken from samples, we were able to extend the inversion from P and S velocities to shear modulus and Young's modulus. And I have plotted here at the bottom of each graph typical values of the graph. Now, we were also measuring velocities as well as elastic parameters based on logging, sonic logging performed in boreholes close to the seismic test areas. And the ranges of velocities and of the Young's modulus are extremely similar with what we have been found, with what has been found in the tomographic inversion. Therefore, we will conclude that the values which we see in the tomograms are correct. But we don't know at this point whether these shapes and these velocity distributions here mean something real or not. In order to ascertain that, we have been plotting, superposed, the tomograms and the migrated profiles for P and S waves, respectively, in order to see what can we say about both, about tomography and migration. Well, the first thing that we can say is that tomograms are extremely superficial. We cover only a few meters inside the tunnel wall, while by reflection we can cover definitely much more. We can also see that there are correspondences of features identified by reflection that intersect the tunnel and accidents in the seismic velocities. We will conclude then that from the tomographic inversion, the main outcome has been the detection of the EDZ, of the excavation disturbed zone. However, in terms of rock structure, and namely deep rock structure, we will have to rely from now on reflection and on migration. Talking about migration, I would like to present you a migration method which has been recently developed by our team. It is the same image point which we have been talking 20 years ago about, except that now it's 3D, and it is also able to cope with the velocity models and to accommodate diverse modes of propagation. Let us consider a source S, Sm in this case, and the receiver R, Rn in this case. And the propagation path that goes from the source is reflected on the plane P and returns to receiver R. In fact, the plane P does not need to exist anywhere else except in the region where the reflection point is, that is, at the point P. Let us also note that there is associated with the plane P a point called IP in here, the IP being the image of the origin in the given plane. Therefore, if a plane is well defined by its position and orientation, also the point IP will be well defined, and vice versa. There is a clear correspondence, two-way correspondence between the IP space and the orientation space of the plane. Therefore, we can take the energy along the path from Sm through V and to Rn and stack it at the point IP in the IP space. The total amplitude accumulated at point IP is computed by integrating over all reflector points V belonging to the plane P, which this first equation here says in mathematical terms. This is in fact a variation of the radon transform. It's a curved path radon transform, which of course has also an inverse, which is depicted below. And by the inverse transform, we are going to reach that the total accumulated amplitude at point V can be computed by taking the integral over all planes containing V. All planes like this plane P, all orientations going through V, contribute to the amplitude at point V in the inverse transform. Point V being, of course, a point in the real space, and there goes the migration. What we see on the right side, it's just an example how the 3D image point space looks like. We have two sections, one vertical and one horizontal, and we can still see accumulations of high amplitudes, like these red dots, which are in fact reflectors in 3D space. We're going to look now at the result of the image point migration applied to a tunnel section. As we see in this plot, we have constructed a cylinder around the tunnel axis, and on these cylinders we have extended panels at various angles. In fact, we have been constructing 12 separate planes between plus 70 degrees and minus 95 degrees, And this is for the chainage of 3320 to 3310 meters. So it's for the 300 meters section of tunnel. Now, why did we go only one side and not a complete cylinder? Well, because on the other side is the tunnel. And we had to go with pumping energy away from the tunnel. And actually, these angles from -95 to 70 degrees are the ones where the maximum energy goes towards the rock from our experiment. Also in this picture, you're going to notice two light blue circles, which in fact they are spheres. And these represent the P-wave radiation pattern of a source in two cases. The lateral one, when the source is oriented towards the wall, laterally, and the one going down is when the source is used on the tunnel floor. We do have also some tear-shaped lobes, which represent the S-wave radiation pattern. On the right side of the picture, you can see the 12 migrated panels as they were assembled around the tunnel. Now, what did you do with those? Well, as the example is given here, we started digitizing the reflectors which you could detect in each of these panels. And based on this digitized reflector, we reconstructed a 3D fracture model, which is presented on the right side. Now, with this fracture model created, the next step is verification and validation. We took a number of known features of the site, like brittle fracture zones, lithological contacts, hydraulically conductive zones, electrically conductive zones, and a set of long fractures. And we tried to identify these features in the seismic records. Most of them could be confirmed. Looking now at a summary, we see here on the left side the vertical expression of the seismic migrated space, and on the right side a horizontal expression of it. Most of the features in both equations have been recognized as known site features, except some, like for instance the one which is marked here with a red arrow on the bottom of the left picture, which could not be recognized as a site feature because of a lack of data at that depth and location of the site. So this could not be validated by any known knowledge of the site. There were a couple of these which were actually in that situation. I would say that the rate of success of matching new seismic features with known site features is of the order of 80%. 20% represents features that could not be equated because of lack of information. Then we turned to another kind of validation, which is verification across scale. At Olkiluoto, during 20 years, there were about 40 boreholes measured by vertical seismic profiling. And this resulted in a fracture model, which we tried, the part of it which corresponded to the position of the Onkalo site. We tried to superpose on the Onkalo features on our seismic experiment, and we found a very good match. But when saying that, one has to be careful, because we have a very large disparity of resolution. What we see here on the right side is the resolution attainable from a part of a VSP profile, while on the right side of this graph we do have a portion of the tunnel seismic data. The resolution is probably 5 to 8 times better. Therefore, recognizing features as being the same it's not always that easy, because we are going to see always more features and more detail in the tunnel seismics. But perhaps the most interesting example of verification across scales has been obtained by inspecting a regional seismic profile of about 15 kilometer length and 5 kilometer depth, which crossed through the Olkiluoto area. The Olkiluoto area, you could see it here at the left top of the 15 kilometers profile. When zooming this zone out, as it is shown here at the left bottom corner of the slide, we can see a feature which is quite prominent that seems to intersect the Olkiluoto site. And the red arrow is there. When blowing this farther up and adding the tunnel seismic example, we can see that in fact the regional feature seems to correspond fairly well with our unknown feature in the tunnel seismic section. This is not really a cross-verification because of the very large disparity in resolution. However, in this sense which I'm talking about now, so finding a big feature, a large regional feature, into a small investigation, yes, in this sense we could extend it as verification. The opposite would be more difficult. Coming now to the conclusions, we would conclude that most known brittle fracture zones, lithological contacts, hydraulic conductive zones, electrically conductive zones, and long fractures could be confirmed up to 200 meters distance. And I will reiterate that the matching rate approaches 80%. However, interpretation has been challenging due to the large number of features identified. High resolutions means also a large number of features. We know that. And identify with known feature of the site gets more and more complex as the number increases. Building a reliable and detailed model of the geological and hydrological features of the repository area requires that integration is carried out among all geological, hydrological, and geophysical data. Therefore, the seismic expression of the site is only one of the sites that have to be put together to obtain a reliable model. On the practical side, we will conclude that the high-resolution seismic imaging could be performed in noisy tunnel production conditions, and that the signal of good quality and a fairly wide frequency band from 150 to 1500 Hz could be obtained from both the tunnel sources and the percussion drill bit. The seismic surveys along the tunnel can be used economically for rock mass characterization.